hit it. All right, welcome back, everybody. So today we're going to be departing into a new adventure to explore the relational model, intention, extension, and constraints. But first, we need to first clarify a couple of other tangential topics that will give us the necessary yet rudimentary tools for us to determine what's the importance of constraints. So if you remember from last session, just give me a moment. There we go. Sorry. So if you remember from last session, we were concerned with the history of the relational model, where we are in the industry, and where we are headed, and how this trend needs to be needs to be scratched, and we need to understand better the formulations instead of just trying to fix current products that are in place. So today we're going to get started with first what is a actual relation. That's a topic that in my experience, a lot of people claim to know, but I think they lack fundamental understanding to say so. And relational algebra operators. So another one of those, and I'm going to make a comparison with Sakura's current implementation, SQL, and go over the operators. And if we still have time, I think I will go at least on intention versus extension. And then later on, we're going to go over constraints, cardinality, and all the jazz. So, all right. So first, what is a relation mathematically? So when we are talking about the relational model, we're basically concerned with an applied theory. I think I mentioned this already, but the RDM is a applied theory of set that attempts to use set expressing things with simple set theory alongside first order predicate logic. So there's a reason for that choice, specifically for first order predicate logic, because we're not concerned with, we don't want actually paradoxes and higher order predicates that may end up in haltability problems. So since we are operating under data and trying to make decisions over data, the simplicity of first order predicate logic is enough for us to express I would dare to say all the possible components that exist in reality in a way that might be a bit cumbersome in a lot of ways, but it gives you a lot of and a lot of safety and good guarantees for you to operate that with a decision engine. So now, what is a relation? So we first need to construct the terms. I'll try here to construct from set theory. I think that will make more sense, and then we're going to jump to predicates. So think of a relation as a subset of a Cartesian product of other sets. So these sets we're talking about, they are domains. So there are three components here we got to go over. So what is first a domain? What is a Cartesian product of such domains? And what is then a subset of those things? So let's go backtracking. So a domain is essentially a primitive in your world of assumptions. So if you recall the conceptual model is concerned with business rules and intents that actors in the real world will have with your system. So those would be, let's say, a business or corporation, a library. Imagine you're doing a library catalog software, or you're doing something more complicated, like rocket. You're launching a rocket and you need to save mathematical calculations. I don't know. So in any of these occasions, there is the primary concern, which is acquiescing with your business rules. So those would be the actual predicates that you need to inject in your system somehow. Those are the things that will derive and produce a bridge between the actual conceptual model and a logical model through some shared meaning. So you need to enforce the meaning that you want onto the computer. So the computer by itself, it just manipulates symbols. We are concerned with actually representing and reverberating such symbols with careful, tailored constraints so they represent exactly what we want. So the domains are the things that we are going to use as building blocks. Imagine like Lego, but they're not really part of the they're part of the axioms that we are going to inject in our world of assumptions, but they're not really core to the definition of meaning. So, for example, age, well, we know that age, like humans generally live in a span from 0 to 120. There's some outliers, of course, but generally, let's set the age. So when we are talking about humans and their age, well, we're talking about their range, but that range is represented by some other primitive that is a subset of such. So in that case, naturals. So we can make a subset age out of naturals that will limit with a constraint that limits it to 120. So that's one example. If we're talking about age of buildings, let's say, well, buildings they can stand ad infinitum, right? So they would be just naturals. So these domains they are essentially these primitive objects for us to construct parts of our design that are not really part of the meaning of the design. Does that make sense? Does anybody have any questions so far?
No, we are using the
Okay.
primitive sets as the way to encode the things that we care about.
That's exactly it. So they're part of the logical theory, right? The logical formulation that we're trying to build.
I have
All
a
right.
question though.
So yeah,
It may be bullshit though, so I apologize in advance.
go.
So man, I was kind of thinking, is it fair to say that like you have the primitive sets and we compose them in a particular manner to
Hmm.
create more advanced and more meaningful things? So then should we say that as like type theory is the backbone of backend programming, relational theory is the backbone of the data? Am I
I
crazy?
think that's a fairly good observation. I like in fact, for example, if you pick, I think we're gonna go over there still, but if you pick something from type systems like system F omega, for example, so we're interested on kinds, right? Well, what are actually kinds in this context? They are the existential quantifiers.
Yeah, for sure.
So, uh, but then you're concerned of how do you make those existential quantifiers uh, comply with first order predicate logic, right? That's another question you should make. But yes, I think the parallel is very good because when we're talking about data, we're talking about like if you think of the like I think the Wadler's distinction, right, is predicates are types. Uh, what's the parallels he makes? Predicates as types, values as proofs. I think that's it, right? So the values are essentially just the things that you prove at the execution level, right? The runtime. That's what I remember on this talk.
Hmm.
Um, so in here we already are dealing with the facts. So, but there's no runtime, right? They are just facts in the world. So we're managing information and questions about the information that are also predicates, therefore also uh, uh, analogous to a proof in a code, right? The code is also trying to express meaning when we run it. Otherwise, it's just garbage on a computer, right? So the connection, I think, is there. We need to give some thought, though. But yeah, I think mathematically the concepts totally match. But
Yeah,
uh,
because my intuition was like, okay, I have a natural or I have an integer. How do I
right.
compose that? I make a record or an ADT.
Hmm.
How do I do the same here? Oh, I make a relation.
Well, and then you may ask, what is a record in your language, right? What is the record trying to do?
Yeah, exactly. So if you question even further, you may see that, oh, the record is another attempt of making a relation.
I think that well, there are just different ways of encoding with different purposes. I would say.
Oh, but there's a difference though, because usually when you're doing the record thingy, and on the in the ADTs, you're not really worried about the principle of normalization. So, for example, you
That,
can't put a maybe in a field of a record, even though that being nullable would be fucked in a relation thing.
well, there is. I think that's okay. That's a nice topic that you mentioned. I mean, we're still going to go over normalization, but I think what's interesting of what you said is this. Can you see that the relational model is at least attempting to to not like null, for example? What is null? Well, null is not part of first order predicate logic, right? So it's not an encoding here. What most languages have as null, they are actually just physical implementations that they added on the runtime of the language to as escape hatch most of the times. Some languages don't even have that, like OCaml, right? SML. Uh, I think Haskell doesn't either.
No, no,
I
no.
mean,
But the
you can
nullable things in
perform
those
it, but
languages would be the maybe thing, right?
well, no. I mean, no, because that's not representing ambiguity, right? It is either that or this. It is just a junction. No is I don't know.
No, yeah, I agree with that. That the escape, the Hellgate being opened by nulls in the relational model is worse. But that's what I was trying to convey. That when you're doing records and ADTs and like you make composited types, you're usually not worried about the things that you should be worried about in a normalization context.
Well,
Like,
my
believe it or
concern is
not, this
this
actually
because
pushes me to believe that Rich Hickey was kind of right in the maybe not talk thing. Because remember
uh,
what he said, that he doesn't like
hmm.
nullables because he rather not have the thing in the map. That is kind of like similar to what we push when you talk about relational databases, right? You should not have a null there. You should not have it at all. That's not a fact.
I well, I think we can save that for another time, but I kind of disagree with that to be honest.
With what part?
Because having the possibility there on a record is not the same as putting null on a column, let's say, as an attribute of something.
Oh, okay. Then we have to pause here because I will ask how come you see the difference, but I don't
Okay.
want to open the tangent too long. So
Let's do the following. Let's continue and then save this, like put it on the chat, and then we can come back to it.
I have a quick question before we proceed. Has anyone tried to do a type theoretic foundation for relational theory?
I don't. I mean, I maybe. I actually don't know. I would wager that no.
Okay.
Although I think it is fairly possible, to be honest. Okay, I'll think about that. But I maybe. My name made me curious now. Okay, so back to what I was saying. Like the okay, continuing. So uh, a domain is essentially parts of the primitives that you may use to compose other things on top of it. And then you can compose those things with a Cartesian product, and then you derive essentially a n tuple, right? So those are basically all the possible combinations that will exist in this realm that derive out of these different domains as a subset. So relation R is essentially an n tuple d1 to dn where di belongs to the domains. That's fairly straightforward, right? So basically, when we are modeling like an employee, we're gonna think of what's the age of the employee, what's the salary of the employee, what's the department ID of the employee, what's his name, and etc. So those would be the things. Now, there's one thing here very important though. So when you say Cartesian product, it may imply the notion of order, right? So the D1 needs to be before D2 and etc. That's not really true. So you can do the Cartesian with all the the D's here, the attributes is crumbled. So they can be through all different combinations, and that shouldn't matter. So an n tuple should essentially just bear the same elements on every element. So every tuple in a relation is unique. So there's a membership to it. So there is implicit here a label for them. So Pascal calls it a named entity. So this D1 here, let's say it would represent the first attribute. So the value for D1 can be anywhere, but there's a label tagging it with D1. So imagine like this. Of course, we tend to just put it in parentheses and follow an order because that's much easier for us to see, right? But that the order is completely irrelevant here. And that's a corollary. I would need to prove it, but forget about it. So that is just because every tuple, this is a set, right? So every element of the set is unique. Therefore, well, the order here should be relevant for that. So anyway, all right. So the order of tuples is irrelevant. The relation is a set. Order of the attributes matter only by the name, not by position. I already mentioned this. No duplicate tuples by definition of a set. Attribute values are atomic, so first normal form. So what does it mean to be atomic? Here is very important because that does not mean that they are like D is a set, right? It's a domain. Now, we could make this with another relation too, right? So you could have a relation derived out of another relation. That should be possible. What's the first normal form saying here is that what normalization actually would mean is that it's following the conceptual model to the T on what it means to be R. I don't want to go too much into that, but you can have structures inside of here and still be in first order, still be normalized. But that doesn't mean that first order form, normal forms, like the first order in the first normal form specifically, is talking about just having an element that is atomic in the sense of their perception in their expression as a value of such domain or relation. It means that their meaning is unambiguous. That's basically what it says. So if you have something, let's say, that is a maybe, it's valid. It's part of a set. So that's why I said that, Lemos. But if something is, let's say, a possible list of telephones, well, there might be people that have 0 telephones and there are people that might have 10. But if only there's a possibility of 0 and 1, then you may rethink that. But either way, let's get that out of the conversation for now. That's on the topic now. So essentially a binary relation, which is what most of the time we are concerned with, is a relation that has basically two. You can think of it as two variables filling a predicate. So less than is a good example. So if we define the less than relation atop of a Cartesian of naturals, we're going to have pairs, like the tuple here, of x, y, where x needs to be less than y, where both are for naturals. So this is an infinite relation in the sense of, by the way, relations, they are, I'm using this as cardinality. In reality, this would be L of 0, right? But consider just infinite for now. So an infinite relation, that means, actually, wait, you cannot enumerate it, but it's perfectly well defined. That is actually incorrect. You can enumerate it. I think I was talking about something else.
I
So
guess
forgive
no.
me
Wait, my understanding of what you tried to mean here is that you cannot enumerate it at all, but you can verify it in finite time.
Um, that's not really what I meant. I mean, I think I was typing here. I had an example, but then I realized that it was non-enumeratable, and then I
Ah, okay, no,
changed.
I see. Yeah, that's different.
So I think I was using reals, and that was bad, right? But yeah, you can enumerate because you can have a bijection of this guy on naturals, right?
Yeah, yeah, sure, 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 sure.
So anyway, okay, so that's basically a binary relation. So mark this in your head. I'll bring that again when I talk about the operators. So operators, essentially in relational algebra, which is the language that we use, the algebra we use to
Pause there.
manipulate.
Sorry,
Yeah,
Brigitte.
go.
I just want to make a highlight here because I think it matters to ground the conversation if somebody's crazy enough to watch this later. If you scroll up, I would like to make the highlight in the less than relation there. The thing there with a comma and a parenthesis, we call that thing a tuple, and it's very important. So the relation is going to be creating, like spitting out valid tuples.
Yeah, it's a set that spits elements that belong to it, right?
Exactly. So because I want to use those terms because it kind of may seem very abstract at first because you're talking about sets and Cartesian products using the. Well, I know you're doing using those because you're trying to be precise, not because you like to use fancy terms. But people will understand that you want to use fancy terms. So I'm just
That
explaining that
makes
this
sense.
is a tuple, and that's
Yeah,
what it
and
means.
this notation here is just to define a set, right? I can define in natural language. So less than is the pairs that where x is less than y. I could have written that, right? But that's like there's a lot of problems when you just
Yeah, natural language is bad for specifying things in this nature.
yeah. So, but notice that this is a predicate, right? So, a less than relation is a relation such that there is a element A that is less than B. So A and B are variables in my predicate, essentially, right? So I need to fill them with values that make it true. So
Yeah, yeah,
that's essentially what it is.
yeah, yeah, yeah.
Another option would be listing values, right? But since this is infinite, I would be listing forever. So,
Yeah, that's also true.
okay, so let's continue. So we're talking here about essentially a closure. So when we are talking about the relational algebra, people have the impression of the SQL stuff because at least when they learn, that's how I learned. I remember like just using SQL and maybe some symbols, but essentially it was all based on SQL. And I think SQL is a horrible uh, language for this because it's not really precise on the terminology and well on purpose on a lot of times. Uh, but when we are talking about those elements, we're talking about this closure. So think of an operation. So when we do something in mathematics like a plus b, well, we get a return, right? And then we can handle that expression as a element somewhere else, right? So it's like substitution. So relational uh, lambda calculus, for example, is very nice to see that, right? You just substitute a variable with what it represents, and then poof, you generate another expression, evaluate it, generates another expression, evaluate it. So you can make recursion, you can make a lot of things with that, right? So here it's here that's an algebraic way to represent things, and not just an arithmetic way. I think we tend to think of make a calculation, get the result, that's it, right? But in this case, we're talking about more of an evaluation. So, what what are the expressions instead of statements? I think that's the fundamental shift. When we use SQL, we're thinking of just statements, and that's what I hate about it. So, in this query here, like select name, age from employees where age greater than 30. Now, that does not produce, so the result set is not really a set, right? It is just it doesn't have schema constraints. It doesn't have any domain declaration. It will type check, right, to some extent, and you can rely on the invariant that age will be constrained to greater than 30, but this constraint is not generated and imputed on a value because there's no such value. It's just a string of results that you get out of it. So it's a form of an iterator if you think about it. It's just a cursor going there, moving it, and spitting results back to a spreadsheet. Let's say that's basically what it is. So
Okay,
that's what I call.
another
Yeah, go.
pause. Sorry, Maggot, to interrupt you. It's very important to say that yes, you can interpret the result of the select as the quote unquote result set, and you may say, oh, even though it's not true, I can try to like live in the illusion that it is. The problem is that there are a couple of times, especially if we're doing like nested queries and things like that the illusion falls apart. And that's the
Mhm.
problem. It's when you are dealing, the language allows you to break the abstraction and leak its details so you are convinced that you are not actually dealing with result relation out of the select. You're actually doing with a cursor.
Yeah, I
That's
think
the problem.
this sentence here says it all. So it treats query results as second-class citizens. They are data dumps, not proper relations.
Yeah,
That's what they
exactly.
are, right? This is the
Exactly.
extension. Like I'll go into that, but extension is essentially the data. Intention is the a set of constraints that I should enforce because that's the meaning. And then Sakura, which I might introduce later. But Sakura is our relational. Uh, it's our relational algebra engine, and every operator in Carta essentially produces an actual relation. So this is a record that we treat all relations in there. So you can bet that uh, every manipulation you can make in Sakura will result into a relation that you can also manipulate equally. So I call those ephemeral relations because they're essentially not relations that are registered in the database. They're just a variable that resulted out of another manipulation. So a query, like a that select I gave you just now, this should generate another relation that you can manipulate, for example. So that would be an ephemeral relation. Um, so they exist only as algebraic objects rather than persisted tables. So tables again are the extension in that case. So you can basically use them with well your schema, constraints, cardinality, generators, provenance, and lineage. They have all the goodies that a relation in a applied RDM should have. We're gonna go over what each of these are later, just mentioning them here for now. Briefly, the schema is basically the well, I don't think I need to explain what a schema is, but it's essentially the schematics. That's a terrible description, but that enforces you the types of your domains, right? So this relation should have these attributes with, and these attributes contain this type and this label. So that's basically it. A constraint uh, is essentially just a four levels of constraints, actually five. So the domain is a constraint, right? So if I declare something is an integer, it better be an integer and not a string. Then you have first order properties constraints, which are essentially just analogous to a check, right, on an attribute. So greater than, I said here, right, greater than 30, this is a first order property because it's basically a constraint in a single property, in a single attribute, age. Then you have second order, which are basically operating as a tuple. So those would be like unique. Then you have third order and fourth order, which are a bit trickier to represent. So I will ignore them for now. Uh, we have cardinality. So cardinalities, they can be computed or estimated. So uh, things that have a bijection on naturals, they are LF0. So they are infinite, but you can still represent them because it's countable. You can't infinitely list them and make it haltable, but you can operate within reason with those elements and use them as domains, for example. Um, Now, of course, this is a lie in a computer because computers are limited, right? So, for example, floats, they're not really reals. Reals, they are continuum, right? That's their cardinality. So they're uncountable, infinite. So you can't really count, so you cannot enumerate them, uh, and they are basically infinite. So essentially, floats, they are trying to mimic real numbers, but they're not really real numbers because they're bound by the number of bits, right, that you have. So they're actually finite. But from the computer perspective, we just ignored those details. So naturals, they end right. You have a bit limitation. Well, it gets counterproductive to represent too large numbers. So that's basically it. And computed are essentially the relations that you are tracking on your system as facts, right? So those are the predicates that you own in your system that are true. So how many users do I have? Well, that's the cardinality of the users relation, right? So that's basically something that is mutable on demand because you learned about new facts in the future and then you just recompute it. A generator, so that's just a physical implementation detail. So that's for lazy evaluation. Uh, Provenance, so that's basically tracking, that's part of the constraints and implying meaning and intention. So that is basically to track where things are coming from. And lineage, which is what produced this relation. So I'll hope to make this more important in the future. All right, so let's go to the actual operators. Does anybody want to make a comment?
I guess it's only worthwhile to comment that if you have lineage and provenance, as you already explained to me and Marinho, you already gain things for free, such as the updatable views
Yep.
and being able to inherit constraints, because apparently the result of a join should also respect the original constraints.
Yes, they should be relations too, right? So,
Yeah, but
indeed.
the funny thing about that is that like every time I remember what you just explained that day, I was like, man, but if I have a relation 1 that is constrained up the butt, and I have a relation 2 which is also constrained up the butt,
Mhm.
how is it possible to create a relation 3 out of the previous 2 that is disrespecting the constraints from the original parents?
Uh, the operators, I cannot think of an operator that allows you to do so in relational algebra.
Yeah, but
The
if
fact
that's
that,
true, why are we reinforcing
like,
the constraint check in the join result?
so here's the thing. There's a so when let's talk about SQL, right, as an example. So when I let's suppose that I have two relations, two tables, let's put it that way. And those two tables they have a constraint on two different values that I'm going to join, right? So it's departments and employees, and I join
Obviously.
based on the department ID, right?
Mm-hmm.
And then the join the department ID will give employee and the department they belong, right?
Yeah.
And there is a constraint on the attribute of a employee and a constraint on the attribute of a department. So they
Yeah.
should be propagated. Now, when you generate that, it will generate the data, right? So the data is correct because the constraints existed up to that point that I used that query.
Yeah.
So, but when you have, like, now, suppose that I get that data, save on a CSV, and I load it back to the computer. Do I have those constraints?
No, no.
They are manifested there, right? As the original, as per their original generation. But
Yeah.
if I try to make a new table that is like employees and departments, and I load that CSV on that table and I start inserting on that, then I might break that constraint. It doesn't mean the same thing as it originally did.
Oh, okay. So actually, what you we're talking about is that you are using the outcome of the join as its own thing, like it's standing on
Exactly.
its own foot.
That's
That
exactly it.
that's gonna be fucked up in SQL.
So what it can give you, and that's already good enough for most people, I suppose. is already just give you the correct thing. But that's not incorporating meaning, and that's not a very expressive system as for you to manipulate and generate things. So a view, for example, just expresses constraints insofar as they are manifested on the base tables, and that's it. Now,
Okay,
it just
yeah, I
so
see.
happens that views are always generated based on their father, their their parent tables, right?
Yeah,
So they are going to be loaded and so forth. But they're not really an algebra. Like they're not the same thing as a relation. They're
yeah.
not. I
You
mean,
are
they should be.
using allegedly first-class citizens to create a second-class citizen, and that's
They're
the
not a
problem.
variable, right? That's the gotcha. I think lacks for this. They're not a variable. I cannot pick a view, put it on a variable, and manipulate it around.
Yeah, no, no, I totally see the point now. I totally see. Maninho,
All
want
right.
to say something?
Um, just another example. What if you take a join and you want to register the result of that join as a view, and then you want to update it? You would need the constraints then, right, to make sure the update is correct.
Yeah, yeah.
Yes.
Updatable views is, yeah, that's also true. Yeah, I was being more simple in my example, and that was the reason I was being blindfolded by myself. But yeah, you guys are right. If you're using the result of the join to something else, not only doing the join, but you are saving it somewhere, you want to load it back, you want to make it updatable view, then you are completely and utterly fucked.
That's a way to put it.
Yeah.
All right. So let's talk first about select, right? So select is essentially not a select from SQL. It's actually a where, right, in SQL, but it is about filtering tuples. So when filtering a tuple, so we filter by a predicate, which is basically a function. You can picture that way. When we say predicate, we mean like a function, right? So the output will be the same schema that you originally had, but it's just a subset of this relation. So that's what the sigma operator does. It's essentially just generating a subset of such uh, of the original relation with an additional constraint. What is the additional constraint? This new predicate. So when I do select employees fund this is a new constraint. This is part of the meaning of what it means to be this new result thing here. So that is essentially just the this result uh, relation is essentially just the employees over age 30. That's the new predicate, right? So it now exists in our database as a new algebra, as a new variable in your algebra, right? So they share the same schema, and they now include the new constraint apart from the original constraints that this had, in theory. And it also has a new lineage because it came, this thing was originated based on a select out of this predicate using this base table employees, base relation, sorry, employees. Any questions? Does this make sense? I think it's pretty straightforward.
Yeah, no, this is pretty okay.
All right. So pi. So that is basically about projecting certain elements out of a relation. So that is basically a that is the selecting sequel, right? So we're basically trying to project only a specific subset of the header of a relation. So think about employees. Well, we have a lot of things in an employee, right? Department ID, salary name, their own ID, email, name. I've already said name, but anyway, you got the idea. So the project should only generate part of that relation, not the whole. Now the schema here diverges because we're not talking anymore about the full employee. We're only talking about the employee with a different context, right? So in this case here, project the name and salary out of employees. So this is not the same relation at all, the result of here. This is another one. So that will be represented on the schema changing. So its type changed. So only the constraints that are now relevant for these guys should be transmitted, right? So if I have a constraint, let's say a referential integrity constraint on the department ID, right? So an employee needs to be assigned to a department. Well, that is irrelevant for this relation. That is only for the relation employee and department. Uh, and then the lineage is essentially just the project with the two elements uh, and the base employees. Now, pretty simple as well. Join. Now, joins are a bit tricky, and I still didn't get them right on Sakura. So, yeah, but I'll try to make my best on explaining it. So, when you do a join, essentially, a join is relying on a single shared point uh, of knowledge between two different predicates, that is, relations in this case, to generate a new relation that attempts to represent a shared context that they express, they manifest. So the employees and departments means that I'm generating a new relation with their employees and their respective departments. So that's a new relation, but it's just a derived relation out of those two. And then the natural join, which is the plain join, it basically relies on the department ID. So that's the bow tie symbol here. So that just relies on the department ID. Um, Now, notice that the schema in this case, it is merged from both cases. The constraints, they are then also merged with an end, right? So we basically just loop over them with an end. And the lineage is essentially just both of them. Now, there's a problem here, and I'm still studying how to represent this properly. So when Cod designed this, he basically did like this. Like that was the semantics that Cod intended. But there's a problem because if you have two things in fifth normal form, which is the actual state that you want your things to be, because if they are in fifth normal form, that means they are everything depends only on the key and nothing but the key. So everything is mapped to do its own essence. Therefore, they are an actual relation because everything is unique on the tuple, right? Everything just represents a single tuple in itself, and they map to what it means to be that relation should begin with. Um, they don't that is another way to say they don't depend on something else other than the meaning of
Yeah.
this relation
Yeah, we
for
have a
that to be.
problem.
That's yeah, go.
We have to work on, like, when I say we, I mean we three. We have to figure out how are we going to explain this to somebody else, because
That might be the
it's
case.
it's very problematic that we still are, well, we rely on the on vague terms such as like
Hmm.
essence and stuff like that because we understand what that means,
Right.
but not like they are considered vague for a reason, which means that we should strive to find a way to explain this in a more tangible way
So
for people that are not used to that.
I'll try to use. Do you guys know about Onto UML?
I don't, but probably Marino does.
Uh, Categories Aristotle. Oops, mistyped it.
I think you mentioned it at some point.
Probably did. It's
Okay, but for now, like I don't want us to go
uh
to this to a tangent, but I just want to like explicitly say
here.
when Magetta says everything is based on the key and only the key, it means that you found what actually makes that thing identifiable.
Yes. So
Like
that's what I
it's
meant
the
with the.
pinnacle of non-ambiguity.
So when I say to you like what is a cat? Well, you may say things that are attributes of a cat because you understand what those attributes are, right? But there is an implicit ontological commitment to the object cat. So if I ask you, okay, apart from those, like you tell me, oh well, it's an animal with fur, two pointy ears, and a tail. And then I look at a sphinx cat, and I say, okay, it has a tail, it has two pointy ears, but it doesn't have fur. And then, is that a cat? Well, don't know. And then you look at a raccoon. Raccoons don't have pointy ears, I suppose, right? But anyway, you look at a
Wait, they
raccoon.
don't?
Well,
Am I
do they? I don't
misremembering?
know. Actually, good question. Raccoon. Oops, I mistyped. Man, my
Dogs.
keyboard is
Dogs have pointy ears.
okay. They do. So a raccoon is a raccoon a cat? Well, I don't know. They kind of look like,
Yeah, but dogs
but they're
also can have
definitely not a
pointy
cat.
ears. Marinho is right.
Yeah, dogs as well. But or you look at a tanuki, right? That's even better.
Yeah, essentially, like in summary, Mageta is bringing up the Theseus ship thingy, and that's. I understand that this may seem unrelated, but it is. Believe us, it's
Yeah, the
totally
point
related.
is what these things. Yeah, tanukis, for example, for I brought them up because they're actually dogs, right? They're not raccoons. So anyway, the thing here is, by the way, this website is really nice. It basically does UML models for philosophy.
Yeah, I kind of like,
Uh,
man, why are they using UML?
yes, that's why it's onto UML, right? That's anyway.
Okay.
So basically, think of the things as what's the core thing that determines what that is, right? So that it's its form in philosophy, at least in classical philosophy. So that is the form of something. So that is the immaterial form that manifests in the specific instances you have in reality. So a triangle will essentially have a universal in that case called triangularity. So that triangularity is the form of a triangle, and every triangle needs to conform with that. We happen to know how to define them mathematically, and that's very nice. Those are 3 points forming a 180 in their sum of the angles of their internal angles. So that's nice because we can actually, with the rule, generate an infinite amount of triangles, right? But they all express the same core rule. So with that core, how do we represent the other properties of that instance? Because remember, when I draw a triangle, well, there's a lot of a noise in the triangle apart from its essence, right? Of its substance of that specific triangle. So substance is simply what that is, and that would be the tanuki, right? So it's a dog. Uh, but then there's attributes that it shares with that it may share with other beings, right? Like having fur. Like a lot of animals have fur, right? But that's not an essential part of being a tanuki. I mean, you may say it is. I don't know.
Yeah,
But anyway, I
yeah,
never seen a naked
yeah. We
tanuki,
should
right?
also, okay, so again, a disclaimer. We may sound crazy, but believe us, those things are related. That's the first. And
Yeah.
second, sometimes it's actually useful to define things in terms of their properties. So that's what category theory does. So we don't have the
Yes.
definition of a
That,
thing, but we have the definition of its morphisms and stuff like that.
that's what we are doing here. There's two ontological commitments. There's the ontological commitment to properties and uh, objects. I'll bring more into detail for when it gets to time. But essentially, it's basically assuming one thing exists and just attuning yourself to other aspects of it. So when we're modeling, we think of properties, right? It's very useful for us to look at like colors, for example. Imagine you're doing a software that is for uh, let's say colors in a for an artist, right? So like it's a drawing board for an artist. Then you have specific like colors. They're not primitives per se, right? They're not just red, blue, whatever. They have a hue. They have a wavelength. They have uh, I
They
don't know
have
what other
properties, yeah.
attribute.
They
Yeah, they
have
have
they have
properties.
things about them.
Yeah, it's easy to see that they do, right, in that case. But if you're just thinking of like a selector in a store for you to choose like clothes in a specific color, like shirts, like t-shirts, then they can be just categorical, right? They can be just 10. So they're still attributes, but they're different kinds of attributes depending on color. So color can shift from being an attribute itself, from being a property, to being an object. in both
Yeah.
cases, depending
Yeah,
on
yeah.
how you look
Yeah,
at it.
that depends on the business domain and what you care about and
Yeah,
about the whole
yeah, that depends on the conceptual model,
the
right?
conceptual
What you're
model.
trying
That's
to
the word I
model.
was looking for. Anyway, I just
So,
want to highlight this is because if we plan on doing like explaining this to people at the end of the year, we have to improve our
oh yes,
ability to
indeed.
explain this without smashing Aristotle to the audience.
Do you think this would help? I
I
think it
have
might, unironically.
I have to think about it, man. It's so freaking hard to talk about those things because here's the threat, okay? Our threat is the toxic pragmatism that will accuse us of doing intellectual masturbation. This is the threat. We have to
Ay,
be able
ay.
to defend ourselves against those people. That's the
It's
problem.
it's the millennium problem, right? It's a problem of the millennia, indeed. Anyway,
Because we are trying to say that the theory matters. So they are already looking at us mad because you're saying
it's
that.
it, it's absurd to me. I have to explain that, but okay.
No, it
Uh,
is absurd by definition, but well, this is the world we live in.
okay. I'll try to cut to the point here, and then
Yeah,
we
sure.
think of how to. So, essentially, that substance would be the key because that's trying to represent what that thing is, right? What is a tuple? If I'm inserting users, what differentiates a user from somewhere else? Right? All tuples must be unique, but what do I have to represent what is this user about? So that is the key. And if I have some other attributes that does not only depend on the key for me to extract its meaning, then it's not normalized. That's the whole point. So anyway, because the key is deriving meaning, right? That's basically it. So there is a problem with this join formulation, and that's what I will revisit in the future. Because do you see that I may generate a join of two things that might depend, like what is the key of employees and departments? Now this is a relation, right? So what the heck is the key of this guy? Is it only the combination of both keys? I don't know. I need to think about that. So you may end up generating something that is denormalized on this join. So that's a problem.
Wait a
But
moment.
that's a problem for the
Is
migrate of the
that
future.
mechanically identifiable? That sounds hard.
I I think I think so because in the worst case scenario, you might just return both here with a shared set, but return the accidental effects because there's a distinction between accidents in the substance and the substance. So you may
Mm-hmm.
generate a relation for accidents and a relation for the substance. The substance is the joined attributes of the key, and then the accidents are just a normal relation with all of them. But those are options. Yeah, I need to think about those, how to actually handle with those in
Well,
a way
I
that
thought that the
that
worst
doesn't
case
suck
scenario would
to the
make
user.
the entire role the key.
Well, that doesn't mean it's while that might solve semantically, that doesn't mean that it is indeed the
Yeah, it feels
uh,
like a hack.
meaning. Yes, it is not because the making them unique. Does that mean that it's actually part of the meaning? Well, don't know. Maybe not. Right. So it's a bit tricky. Anyway, so that's the join. That's still we're still thinking of what to do with it, but that's essentially it. How code does it. Now there is theta joins. So theta joins they are basically joins under a predicate. So the same fashion as the select the where right. We produce the new resulting table. Sorry, resulting relation, but we have additional constraints for them. So department ID from both needs to be equal. So I'm joining based on this guy, and the salary needs to be greater than the budget. Now, this constraint here is dumb, right? Because that's just an attribute for the join. So you don't need to create an actual constraint in this guy for this, right? There should be a tautology. But for this
Question.
guy, you do. Yeah, go.
What is the Like, what is the purpose of theta join aside from convenience, given that this is just a project and a select composed?
Uh, you may want to join things that are not because the natural join you're joining based on the name, right? On the label, sorry, on the attribute. So the name and the type must be the same, right? So for both.
Ah, okay, so the theta join allows you to not do a natural join.
Yeah, in this case here, for example, I just want the employees which the salary does not exceed 100th of the budget of the whole department
Yeah, no, but you could do this using
or
a natural
exceeds.
join and
Okay.
then a select, and you're done, right? A select on the
Yes, I
result
could.
relation.
Yes, I could. But I wouldn't. But notice, I would end up with the same relation with the same constraint.
Yeah, no, but that's what I said about convenience. But then you highlighted that the join, the first join, is necessarily a natural one, and because you
Mhm.
have a full lambda here, you can actually do a join on other things.
Yes. So I could generate with these, right? But then I would need to use a the select to the where, right, to filter this out.
Yeah, no, yeah, but
Yeah. So you would end up nesting the
yeah,
thing here.
theta joins actually require the whole fifth normal form thing to be inherited and such, because you can join with whatever you want. That may
Yep.
create some
They're very
situations that
dangerous.
are fucked up.
They are very dangerous. Yes. Uh. Okay. So there's other things like they are more useless. Like I mean, they're not useless, but they're kind of trivial, right? Like rename the row. You basically change the thing. May seem very dummy. Like, why would I want this? But think about it. I'm actually changing the type of something.
Yeah, you're changing the scoping thing, right?
Yeah,
Because
because the
otherwise shadowing
attribute
would be a problem.
shadowing is a problem, yes, but it's not just for shadowing, right? It's more about the predicate that I'm trying to convey. Because if I have a new relation and there's a name field there, well, I might know where the name came from, and that came from the employee. But does the name of the employee being named in here make sense for this predicate? You see, that's the question I have to make for the naming in this case. Since we have lineage and provenance, may be the it may be sufficient, right, for this case. But if you have something that is named ambiguously, think that it's named ambiguously as a predicate as well. So when you compose this, like let's say employees are let's see, so uh, they have people with age, departments, and salary, right? So employees are people employed uh, with a salary X, a name Y, and an age blah blah blah, working for a department X, right? So if I have just employees are people working for a department X with I don't know, and then I don't have age properly named, then I don't know, being a milkshake with milkshake 10. Like, does that make sense? Not really, right? So naming things is important because that's actually part of the meaning as an attribute
Yeah, no,
here.
but
But
what I
that's just
meant by saying the shadowing thing is that if you were not doing shadowing at all, every relation would not be able to have the same field name as everybody else. So you would already have employee name in the employee relation.
all right. Yes.
But if you are using name in multiple places because it makes sense on the relation on its own, but you're doing a join,
Mm-hmm.
then it gets messed up because there are multiple names now. Which one is the one
Yeah.
you care about? So then you need a renaming strategy.
I had this problem on the joins because if I'm doing a natural join, that means by definition that there's two things, two attributes named the same in the two relations, right? So what do I do? Do I keep them? Well, they're the same, so I can just
Ooh.
discard them.
Yeah, but that
Right.
opens the scapegoat for something dangerous. Because here's the
That
thing.
makes a lot of things here
Let's
dangerous.
say that you have an attribute that is the same type as the, let's say, primary key, for the lack of a better name for now. And then you use the renaming to change the name of this attribute to the name of the primary key. And then you
Well,
join with
that
that.
that is what I pressed on the rename being actually looking trivial, but it's actually important because that means that by the rename that it's something else. It's not the same thing anymore. It may be the
Yeah.
same attribute at the surface, but the label is important too. That's why the label is part of the attribute. Like there's an actual like on Sakura, I actually made attributes be a container that are parts of the schema. So it's not just like a map. This gives the bad impression, I think. Uh, this is an attribute. This is an attribute. You see, so it is the both the name and the string. Now the fact that I might have like relabeled this, that means that it's another attribute. It means something else.
Yeah. No,
So
yeah,
I
that makes
lost the
sense.
original meaning, right? Okay. So next,
Cool.
this is one more that I did. It's actually kind of so. This is basically to manipulate the cardinality of these things. So in a perfect world, this would be random, right? So take 10 values out of a lazy thing, it should give you 10 random things, right? They don't have order. So I should give you just 10 random elements out of this thing. Of course, since we're talking about an applied version of it, I will have. Well, it's nice to have order, which is sort, for example, is not relational. Like it's not a relational operator at all, and that should not matter for you to make queries. But we know it does, right? But I didn't add them here because I didn't want to confuse people. But take I did. So take is essentially just given something with a cardinality, give me this amount from them, and that's it. And that would generate a constraint with the cardinality, right? Instead. All right. So sorting, I mentioned just this. It's not relational. Don't think about sorting, but it's useful because we do want to sort things in the extension, right? In the representation of the data, we want to represent things as sorted. I think I might change this later to move away the sort out of the relational operator and put it only on the extension module because it is not it's not a relational operator at all. It's just a visual representation of a relation, right? Which is important. Not saying it isn't, but don't want to
Yeah, this is
confuse both.
this is basically the exit door. You use it when you're leaving the relational constraints and you're saying, okay, I want to put this on the screen to show it to a user, for instance, right?
Yes, correct. Or give to an application, right? I want the application to have the top 10 most consumed. Um, Actually, that would be a normal relation, but they order the list of, I don't know, uh,
Yeah,
interest payments, whatever.
there are cases where you want it sorted.
Hmm. All right. So notice that all these things they are just expressions. So composing them is not a problem. So we can in in Sakura, we can find the top 5 highest paid employees over 30. So this would be a lot of constraints together, showing only name and salary. So a projection, right? So that would be a projection of name and salary atop of the relation out of the take, sorted with this select, which is the where, atop of these guys here. So that's basically a way to encode this on Sakura. All right. How are we with time? Uh, so far, I think it was
We
just.
we are actually 1 hour and 3 minutes.
I think we should stop then and go at this in another time.
Okay, so I'll finish the
Okay.
recording now. Any
So
other comments
today,
before I finish recording? Uh,
yeah. Just if you aren't to here and this is probably just a trivial and you've seen this in other places already, I would encourage you to at least stick around to the next session because we're gonna actually start something different. So I think this part is not really talked about. So that's basically it.
awesome. Okay, so uh,